35 years ago, Mauna Kea was a desolate, extinct volcano with almost no life on it. Now it's the home of one of the finest and most modern observatories in the world. Here we have the Keck telescope, the largest optical telescope ever made, with its 396-inch segmented mirror. Here we have the UKIRT, United Kingdom Infrared Telescope, which can peer into the dusty regions where stars are being born. And here we have the James Clerk Maxwell Telescope, which sees in a different way again. This is about as high as a man can work efficiently, because we're at nearly 14,000 feet above the Pacific in the island of Hawaii. And your lungs are taking in only about 39% of their normal intake of oxygen, so you have to be very careful. It's been described as halfway to space, but halfway isn't the whole way. We still get clouds here, and you can't control the weather. If you want absolute perfection, you've got to go into space. Since the start of our Sky at Night programs in April 1957, we've seen the beginning of the space age and its development. At the start, the Russians took the lead with their rocket launching ground at Baikonur in Kazakhstan. Last time we did a Sky at Night anniversary, I couldn't come here to Baikonur, which is the most important of the Russian space launching grounds, the equivalent of the American Cape Canaveral, because visitors definitely weren't allowed. From here, almost all the most important Russian space missions have been launched, including the very first one of all, Sputnik 1. It was the first man-made object to orbit the Earth, a tremendous achievement, and it ushered in a whole new era of exploration. The Sputnik, or rather part of its launcher, was well seen as it passed over Britain. But outside Russia, this great 250-foot dish at Jodrell Bank was the only telescope which could track it. In a way, that was lucky, because the telescope was in trouble, and so was the man who masterminded it.
I think a few days before it was launched, I said to one of my colleagues, we needed a miracle to save us, because we were in such disfavor and in so much debt. And that miracle did come on October the 4th, 1957, from behind the Iron Curtain.
Smaller than Sputnik was Explorer 1, America's first artificial satellite, masterminded by Wernher von Braun and launched, like so many others, from Cape Canaveral. It was tremendously important because it led to the discovery of the zones of charged radiation orbiting the Earth, now known as the Van Allen zones, in honor of James Van Allen, the principal investigator. This was really the first major discovery of the space age. Meanwhile, over at Baikonur, the Russians were having great successes. In addition to sending up the first space satellite, the Russians put the first man into space, Yuri Gagarin, in April 1961. But in 1959, they had already started sending unmanned rockets to the moon. Luna 1 went past the moon and sent back important information, such as the fact that the moon has no magnetic field. Luna 2 crash-landed on the moon, and Luna 3 went around the moon and sent back the first pictures of the moon's far side that we can never see from Earth because it's always turned away from us. And we were, in fact, the first to show those pictures on the Sky at Night, because the Russians had sent them straight over. They had, in fact, used my own maps of the moon to correlate the far side pictures with the side of the moon we knew about. But it wasn't only the moon. They also started sending rockets to Mars, with mixed success, and to Venus, and their Venera probes, all 16 of them, had been very successful indeed. They sent back the first actual picture from the surface of Venus. The Venera program was a long one and extremely important. Meanwhile, the Americans were concentrating upon manned flight. I'm at Cape Canaveral, the main American rocket launching ground, and from here, most of the important scientific missions have been sent up. This is a Mercury capsule, less than 9 feet high. And it was in Mercury in May 1961 that Alan Shepard became the first American in space. He made a suborbital hop lasting less than 20 minutes. And then it was also in Mercury that John Glenn completed the first orbit round the Earth by an American. The last Mercury was that flown by Gordon Cooper in 1963, and there the suit he actually wore. He made 22 orbits of the Earth. In turn, Mercury was followed by the Gemini program, which was succeeded by Apollo, the mission for reaching the moon. Just look at the size of the VAB, the Vehicle Assembly Building, much the largest structure on Cape Canaveral, and there are very few larger anywhere in the world. And it's here that the great rockets are assembled before being taken out to the launching pad. The Americans went ahead with their moon program, and it was this, plus the idea of a space race, which really caught the public imagination. On the 16th of July, 1969, the huge Saturn V rocket lifted off, taking 3 men on their way to the moon.
5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
The climax came on July the 20th, when the lunar module touched down on the bleak rocks of the lunar Sea of Tranquility.
Down 2.5. Forward. Forward. Good. 40 feet down, 2.5. Picking up some dust. 30 feet, 2.5 down. Straight shadow. 4 forward. 4 forward. Drifting to the right a little. Down 1/2. 30 seconds forward. Good. Ready? Contact light. Okay, engine stop. Houston, Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
A few hours later, first Neil Armstrong, then Edwin Aldrin, stepped out onto the surface of the moon.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
They found a strange world. I don't think anyone's ever bettered Buzz Aldrin's description of the lunar scene as magnificent desolation. Afterwards, I talked to Neil Armstrong.
The Earth is quite beautiful from space and from the moon. It looks quite small and quite remote, but it's very blue and covered with white lace and, of the clouds, and the continents are clearly seen, although they have very little color from that distance.
You're one of the very, very few people, I think, whose opinion on this is really worth having. In fact, there are only 4 of you. Do you think, from your knowledge of the moon, having been there, that it is going to be possible in the foreseeable future to set up scientific bases there on anything like a large scale?
Oh, I'm quite certain that we'll have such bases in our lifetime, somewhat like the Antarctic stations and similar scientific outposts, continually manned.
This is Mission Control at Houston, Texas, the very heart of the American manned space program. In fact, all the manned flights, including, of course, the Apollos, have been, and still are, controlled from here. Apollo 17 was the last in the series, and this was the most scientific of all, because it took the first qualified scientist to the moon. Of course, all the astronauts knew a great deal about science, but this was different. He was Dr. Harrison Jack Schmitt, who was a geologist and been trained as an astronaut specially for the mission. His knowledge proved invaluable, and when walking around the moon, he made a most interesting discovery.
Wait a minute. What? Where are the reflections? I've been through once. There is orange soil. Well, don't move it till I see it. It's all over. Orange.
For a time, it was thought that this indicated recent lunar volcanic activity. In fact, it didn't. The orange color turned out to be due to very small, ancient orange glassy beads, but fascinating nonetheless. The commander of Apollo 17 was Eugene Cernan.
My overall impressions of the moon are really overshadowed by my impressions of looking back at the Earth. The moon itself it's been called like a sandy beach. It's colorless. It's all those bland things that we think of as being unbeautiful, but it is beautiful. It's majestic. It's got towering mountains, and it's got tremendously overpowering landscape. And yet the most significant thing about being on the moon is to realize you are in effect standing in the middle of a three-dimensional charcoal picture and looking back through the blackness of space, through the blackness of space that is filled with sunlight yet, and looking at the Earth, because the Earth, its life, its color, its beauty, and to me, far beyond even stepping on on the surface of the moon is to think back and look back at home, at our star, at our Earth, at our planet.
Well, the Earth looks beautiful because of its atmosphere, but there's no atmosphere on the moon. I wonder, what was the sky like?
Well, it's hard to imagine that one can look into blackness and be surrounded by sunlight. That's a paradox, but that's exactly what it is. When you are in sunlight on the surface of the moon, if you look and concentrate very, very heartily, you can see stars out there. And of course, you can see predominantly the Earth in its multi-blue colors out there. When you go behind the moon, when you're flying, of course, when we're on the moon, we were in sunlight the whole time. But when we were flying around the moon, we went into darkness, into the shadow of the moon itself. And then you are in probably the blackest black a human being can imagine in his mind. You are out of sight of the Earth. You are out of sight of the reflection of anything except the stars. And there are hundreds and hundreds and hundreds of millions of stars. And it's so black, you cannot even see the surface of the moon that you're flying just maybe 80 kilometers above.
On the moon, the sky is black all the time. There's no air to scatter the sunlight around and make the sky blue. But there's more to it than that. Light is a wave motion, and the distance between one wave crest and the next is called the wavelength. If the wavelength is shorter than that of light, we have ultraviolet, X-rays, and gamma rays. If the wavelength is longer than that of light, we have infrared, microwaves, and radio waves. Most of these, apart from visible light and some of the radio waves, are blocked by the Earth's atmosphere. So from ground level, you can't study them. The higher you go, the less air there is above you to block the radiations. That's why Mauna Kea is so useful. But even here, at nearly 14,000 feet, there's still a good deal of atmosphere above you. And that's why we want to go higher. We want to go into space. And the obvious way is to launch satellites. Satellites have told us more about astronomy than we could ever have learned otherwise. For example, what about X-ray astronomy? That began in 1962 with the discovery of an X-ray source by a rocket. But X-rays can't get down to the Earth from space, and that's why space research methods are essential. By now, many X-ray sources have been discovered. One of these is Cygnus X1, which we believe to be made up of a giant star together with a black hole companion. A black hole being a region of space around an old, collapsed star, which is now pulling so strongly that not even light can get away from it. Material from the giant star is being pulled into the black hole. And as this happens, the material is heated so intensely that it gives off X-rays. And to study these, we need to use satellites. The latest satellite is ROSAT.
Well, ROSAT has been extremely productive. It's increased the number of known X-ray sources and extreme ultraviolet sources by a factor of 100. In addition, many new objects have been discovered. For instance, there are quite a few new supernova remnants that were previously unknown that we found. And at the other extreme in scale, superclusters have been detected, which are now the largest known structures in the whole universe.
Using ROSAT, I gather you've discovered a white dwarf binary. What's the significance of that?
One of the reasons why that's interesting is that white dwarfs, of course, traditionally have been observed as single stars. It's very difficult in the visible part of the spectrum to see them when they're in a close binary system with a bright main sequence star. But with an extreme ultraviolet camera, of course, they show up very well. So I think the bottom line will be that we're finding there are a lot more white dwarfs around, many of them hidden in binary systems than we ever knew of before.
X-ray astronomy is truly international. Can you say something about Ginga and Spectrum X, for example?
Well, Ginga is the project that we have been working on for the last 4 or 5 years, in fact longer than that if you go pre-launch with the Japanese. And it's a project that was highly successful. It was intended to fly for 2 years. It finished up working for nearly 5, and everything worked perfectly until re-entry last October. Spectrum X, or JetX, our part in that, of course, is another international project, and that's one in the future, where we're building this new type of telescope that we hope to fly on a what was a Soviet satellite. It will now be a CIS satellite in the late 1994 period.
Leicester is very much a centre of X-ray astronomy. What are the main aspects of British research?
What sets our program apart, perhaps, from the Americans, the Japanese, the Germans, is that we don't have our own national space program, of course, so it means that we have necessarily to work on an international basis. So probably the thing that's special about the UK program in X-ray astronomy is that it's very broadly international.
Another branch of astronomy that can be studied only from space is ultraviolet. Again, this is because the ultraviolet radiations are blocked by the Earth's atmosphere and can't reach the surface. But ultraviolet astronomy is important. It helps us to understand the most remote stars and star systems. One spacecraft, operated from the Goddard Space Flight Center near Washington, has been working on this for many years. The IUE, or International Ultraviolet Explorer, is controlled from this room. It's the only satellite that's controlled directly in real time, and that's happening at this very moment. The IUE was launched in 1978 with an estimated lifetime of 3 years, but it's still working perfectly and still sending back valuable data.
We observe objects from solar system to stars to galaxies, the whole gamut. One of the things we did very well was looking at supernova 1987A. We were able to get on it in a few hours after it exploded. We were able to identify the progenitor star, and we were able to obtain a complete light curve because we, of course, have no clouds or anything to stop us from continually going through. We have also been instrumental at IUE was discovering that the sun lives inside of a small local little cloud of small extent of interstellar matter, and then there's a big void around it which is free of matter.
What will finally bring it to the end of this glorious career?
Well, it's not absolutely certain, of course. It could die tomorrow, as spacecraft do, but we cannot reverse the degradation of the solar panels. Probably, I don't think we have more than another maybe 3 years, its original mission lifetime on those. We could always have a catastrophic failure. You never know.
Ground control, this is TNC West. Standing by for your pre-pass brief.
Goddard also controls other spacecraft. GROW, the Gamma Ray Observatory. Launched last year, it's already sending back information about bursts of gamma rays from extremely energetic objects. And just a few days ago, COBE, the Cosmic Background Explorer, made what has been called one of the discoveries of the century. It's found evidence of the earliest period in the making of the universe, the seeds which form the galaxies. But nearer home, what of the planets? The first planet to be contacted by a space probe was Venus, way back in 1962 with Mariner 2. And Mariner 2, like all the later American planetary probes, was controlled and monitored from the JPL, or Jet Propulsion Laboratory, at Pasadena in California. And the nerve center is the DSN, or Deep Space Network. And this is an incredible place. It's pure Quatermass. It's here that the signals from the probes are being received, and it's here the commands are sent out to them. And remember, the DSN had been in action 24 hours a day, 365 days a year, for over 30 years now. So what have we learned? Venus first. Well, Venus didn't turn out to be the kind of world we expected. We'd expected to find a good deal of water there. Well, we didn't. What we found was a very hot world indeed, with a temperature not far short of 1,000 degrees Fahrenheit, with a choking atmosphere made of carbon dioxide and clouds made of sulfuric acid. We've learned more since then. The mariners, and of course the Russian Veneerers, some of which made soft landings there, have told us a great deal. But the latest probe, Magellan, should improve on any of these. It's not going to land on Venus. It's going round and round the planet, and it's mapping the surface by radar in more detail than had ever been possible before, and should tell us what Venus as a world is really like.
Well, Magellan is a spacecraft that was launched by NASA on May 4th of 1989, and we arrived at Venus on August 10th of 1990. The spacecraft has one major instrument on board, and that is the radar. You can see this large dish antenna at the top of the spacecraft, and that's the antenna that we use to send radar waves down to the planet's surface. They're reflected back, and from those reflections, we turn those into images. We can't use a conventional camera to image the surface of Venus because you get basically pictures of clouds. Venus is covered by a greenhouse effect, so that you need a radar to penetrate those clouds and produce an image of the surface. We also have an altimeter on board which measures the surface height and allows us to build up a topographic map of the surface.
What's the main point of going to Venus?
Well, Venus is known among scientists as the most Earth-like of the terrestrial planets. And that's because the two planets have about the same mass and about the same density. We think they're composed of about the same material. Now that's important because we think that the size of a planet and what it's made out of have a lot to do with the sort of geologic activity that you see on the planet. Namely, the larger a planet is, the more heat it produces, and heat is what drives geologic processes. So therefore, the geology of the Earth and the geology of Venus might be very similar, allowing us to learn a lot more about the Earth.
What are the main results so far?
We've found many interesting things, many interesting volcanic features. For instance, we found channels that seem to have been thermally eroded, or where the heat of the lava actually cuts down and erodes a channel into the surface. We recently found one of these channels that's about 7,000 kilometers long. These are very unusual features that imply some really unusual compositions and styles of eruption that we don't really understand. So that's been very exciting. We've seen very unusual tectonic features, large rift zones where the crust of the planet seems to be pulling apart, large mountain ranges over 11 kilometers above the surface of the planet. We've seen just so much tectonic activity and so much volcanic activity that we're really still struggling to figure out how this planet works and how it compares to the Earth.
A second probe has been looking at Venus, and this is the impressive Galileo. Frankly, it wasn't meant to. Galileo is a Jupiter mission, and the original plan was to go straight from the Earth to Jupiter. But various cutbacks and difficulty with the launcher meant that the plan had to be altered, and Galileo's had to go by a much more circuitous route, rather like going to Bognor to Brighton via Carlisle. It has had to bypass Venus once and the Earth twice, and in passing Venus, it sent back some useful data. It's also been out into the asteroid belt, and there's been a successful pass last October of the asteroid Gaspra. But I'm afraid there are problems. The high-gain antenna has not deployed properly. Efforts have been made to free it. So far, they've not been successful, but of course, further attempts will be made, and we hope that by the time Galileo reaches Jupiter in December 1995, all will be well. The plan is to put the orbiter into a path round Jupiter to monitor the planet and also the main satellites, while the entry probe will detach itself and go straight down into Jupiter's outer gas, sending back invaluable information in the last few moments of its life before it's destroyed. So let's look forward to the arrival of Galileo at Jupiter in December 1995. Mars has always been regarded as the most interesting of the planets. In the 1960s, unmanned probes were sent there. And then, in the mid-1970s, came two Vikings, which made controlled landings on the Martian surface and sent back the first direct pictures. And this is a full-scale model of a Viking standing upon Mars. They looked carefully for any signs of life. They didn't find any. But many years earlier, in a Sky at Night program, we'd look forward to the possibility of life on Mars.
Now, you'll sometimes hear it said that there may be plant life on Mars. Well, it's rather unlikely, I think, that any of our higher terrestrial plants would survive under Martian conditions, although it's just possible that some very lowly forms, which we've not yet tested, may. But just to show you the fate of higher plants, I brought along tonight two cacti. And you can see these here. This cactus has been quite healthily growing under Earth conditions. And you see it's quite a nice, firm-looking sort of cactus. This one here has spent one night under Martian conditions. And I think you can see without any doubt that it's got a distinctly morning-after appearance.
The myth of the Martian canals was finally laid to rest. And those dark areas were not old seabeds filled with vegetation. They were simply albedo features. But Mars did show massive volcanoes. And there were things there that looked remarkably like old riverbeds, indicating that there must once have been running water upon Mars. But life? Well, in the mid-1970s, the two Viking probes were dispatched, and they came down gently upon Mars and sent back information direct from the surface, and they looked very carefully for any signs of life. They didn't find it, and it does now seem that at the moment anyway, Mars probably hasn't got any life on its surface. It's interesting that although the Russians have had great success with their probes to Venus, they've had no luck at all with Mars. And all their various Mars probes have failed for some reason or other. Even their probes to the larger of Mars's two moons, Phobos. And the idea there was to land on Phobos and literally hop around the surface. But both those Phobos probes went out of contract, one because of human error, a faulty signal sent out from Russia, and the other because of a failure on the probe itself. There were great successes with the outer giants, Jupiter and Saturn. Both these were contacted by the pioneers in the early 1970s, but then came the Voyagers. Voyagers 1 and 2 were launched in 1977. 2 years later, Voyager 1 flew past Jupiter and then went on to a rendezvous with Saturn. Voyager 2 surpassed even this and was possibly the most successful spacecraft of all time. It flew by Jupiter in 1979, Saturn in 1981, Uranus in 1986, and finally Neptune in 1989. And the Jet Propulsion Laboratory here in California is still in touch with it.
Well, certainly at Jupiter, the highlight, the thing which caused the largest revolution in our thinking, was the discovery of 8 active volcanoes on Io. And that, in fact, taught us how important evolution is in the formation and change in these planets. At Saturn, certainly, one of the major surprises was all of the fine structural detail that we discovered in the rings of Saturn. And of course there was Titan itself, where we measured for the first time an atmosphere 60% higher pressure than here on Earth, mainly nitrogen, with interesting hydrocarbon chemistry. There were 2 surprises at Uranus at least. One was the fact that the magnetic field was tilted by some 60 degrees from the rotation axis, the first time we'd ever seen such a thing. And then there was the moon Miranda, a small world only 500 kilometers across, but which had experienced a very intense geologic activity sometime in the past, which significantly changed its surface. At Neptune, we had a number of surprises. So one of the surprises was it also had a tilted magnetic field, but perhaps the highlight of the whole encounter was the moon Triton, the first moon we've seen, which is so cold, almost 400 degrees below 0 Fahrenheit, so cold that its surface has solid nitrogen and solid methane on the surface, and the geology was reminiscent of many objects we'd seen before in the solar system.
Yet the Americans pulled out of one space mission on the grounds of expense, the mission to Halley's Comet. Comets, as I'm sure you know, are insubstantial bodies. Even a large comet is made up of a relatively small, icy nucleus, which starts to evaporate as the comet nears the sun, producing a head and a tail. The most famous of all comets is Halley's, which comes back every 76 years. Halley's comet returned in 1835 and in 1910, so it was expected back to perihelion, its closest point to the sun, in 1986. But to start with, no one knew how bright it was liable to be, and searches for it at all the major observatories began years ahead of time, way back in the 1970s. And when success finally came, the triumph was here at Palomar. With this great telescope, the Palomar 200-inch reflector, the comet was observed in 1982 for the first time since 1911. And surely it's fitting that the most famous of all comets should be recovered after more than 70 years with the world's most famous telescope. And, of course, this was the first return when Halley's Comet was observed by spacecraft. When Halley's Comet was recovered, it was a tiny, dim blur. Even when closest to us, in 1986, it never became bright. But all the same, this was a most important return. 5 spacecraft were sent there. 2 Japanese, 2 Russian, and the European spacecraft Giotto, masterminded from the operations center here at Darmstadt in Germany.
Well, everything went fairly well according to plan. We had beautiful data, when suddenly, just 7 seconds before closest approach, the screens went blank. That was a major disappointment. Another thing that comes back to my mind is the colorful images of the near-nucleus region, which were extremely difficult to interpret. And it was only at 2 o'clock, 3 o'clock in the morning of that night that we saw the first relatively clear black and white images, which showed the outline of the nucleus fairly well. And I remember at 3 o'clock in the morning, I saw my first, as we then called it, crater on the surface of the comet. And for me, this was the ultimate proof that we had actually seen the comet nucleus. The size of the nucleus from one end to the other is about 15 kilometers, the diameter 8 kilometers, and it has this odd shape. It is fairly dark, and it has some very interesting surface features, valleys, mountains, and so on. And to obtain these clear images of the nucleus, I would say, is perhaps the main achievement of the Giotto mission.
But we haven't heard the last of Giotto. It's been reawakened, and on the 10th of July, it will encounter another comet, Grigg-Schellerup. What makes comet Grigg-Schellerup so interesting?
Well, we have visited comet Halley, and now we are visiting a comet which is of a different nature, insofar that Halley is a very active comet, ejecting a lot of gas and has a dust cloud around, whereas Grigg-Schellerup is much less active. It's also much smaller, only 500 to 2,000 meters. That's what the astronomers estimate. And it is interesting to compare both of these comets to see if there's any evolution and what causes difference.
How many of the original instruments are still working?
We originally had 11 scientific instruments on board, fully working. Now, out of these, 7 are still functional and we hope, good scientific data.
Last time you went within about 500 kilometers of your target, Halley's comet. How close will you go this time to comet Grigg-Schellerup?
We will aim direct at the comet nucleus, but we expect that we will pass within 1,000 kilometers of the comet nucleus.
At the technical headquarters of the European Space Agency at Noordwijk in Holland, many successful spacecraft have been built. The latest, Ulysses, was launched in 1990. Last time we were here, it was undergoing its final tests. It's now on its way to the Sun, having passed by Jupiter in February. Jupiter's powerful pull was used to swing Ulysses into the correct orbit for looking at the poles of the Sun. They've never been studied before, but why are they so important?
That is a very good question. As with the Earth, you have the polar regions and the equatorial regions. At the moment, every probe that has been launched, every spacecraft that has been launched, has been almost entirely in the ecliptic plane, and therefore we only get to look at the Sun sideways on. This has been likened by one of the experimenters that's flying on this to trying to understand the physics of the Earth by flying an aeroplane round and round the equator. The poles, just as for the Earth, where we only really understood how the northern lights occurred, was when we started flying spacecraft over the poles and understood how the magnetic field of the Earth worked. In exactly the same way, we need to fly over the poles of the Sun to understand how the Sun works.
It's amazing to think that you and I are standing within a few feet of a probe that's actually going to be launched. It's going to go over the Sun in the near future, and I imagine you're pretty excited about it.
Oh yes, of course. One's always excited and scared too, because space is a risky business. You never know for sure whether it's going to work. There is nothing guaranteed in the space business. So it's a very exciting and very scary time for all of us.
From space, observations can be made which can never be carried out from the Earth's surface because of the shielding effects of the Earth's atmosphere. X-ray astronomy must be done entirely from space, and Skylab carried an X-ray telescope built at Birmingham University.
We've built 2 of them to go into orbit. The first of them was on the NASA Spacelab 2 mission in 1985. That instrument was taken into orbit and operated for about 10 days, and then finally brought back, and we refurbished it, and we're now hoping that we may be able to use it in the run-up to the space station. The second one was placed on the Mir spacecraft of the USSR. That's a space station, in fact, and is intended for long-term operation in space. And so we hope that telescope will go on operating for a considerable period. And it's already been operating for a couple of years.
And Britain had been involved in many other space ventures. In 1983 came the launch of a very special satellite, IRS, the Infrared Astronomical Satellite. It was, of course, unmanned and was an international venture. The information was received and analysed here at the Rutherford Appleton Laboratory in Oxfordshire. It was the first satellite to discover a comet, IRS Araki-Alcock. IRS also found the zodiacal dust bands, which turned out to have considerable structure, probably linked to asteroid families. It found a dust ring around the star Vega, where planets failed to form. It saw stars all the way to the centre of our own galaxy. It found stars forming in galaxies much brighter than ever imagined in the infrared. And the cirrus, the infrared dust in our galaxy, which has obscured the view of stars in the same way as cirrus clouds obscure the view from Earth. As IRS was only designed to last for 9 months, were the astronomers surprised at the wealth of data?
I think we were very surprised at first. You know, before IRAS was launched, at the longest wavelengths you can easily observe from the ground at 11 microns, we had about 2,000 sources known. IRAS in the first 12 hours of operation discovered over 3,000. And so that was a real surprise. I think we were all rather overwhelmed.
There are infrared telescopes on the Earth's surface. Why do you have to go into space?
Well, there are a lot of regions that we want to look at, particularly IRAS showed this, that you can't see from the ground. All these marvellous galaxies we found and these dust shells, they are most bright at wavelengths longer than the ground can observe. And so we really need to go into space. And of course, with our new satellite, the Infrared Space Observatory, we can look at things that we discovered with IRAS, and we can look in the wavelengths that we can't see on the ground, and hopefully we'll find a lot of new objects there.
IRS can do things that no ground-based equipment can do because it's moving above the top of the atmosphere. We now have infrared maps of the whole of the sky. But we also need very accurate maps of things we can see visually. We want to know the precise positions of the stars, and we want to study the ways in which the stars move individually. This can be tackled from ground level, but again, we've been overtaken by space research on a satellite, Hipparcos, built at Noordwijk by the European Space Agency. Actually, Hipparcos was put into the wrong orbit because of a faulty rocket firing, but nevertheless, it has been able to carry out its full program of research.
By measuring the positions very accurately, we can eventually determine the distance to the stars and how the stars are moving through our galaxy. And very many areas of astronomy and astrophysics actually depend rather critically on a detailed knowledge of the distances and the motions of the stars. So this is really what we're trying to get out of the measurements.
Why have these measurements got to be done from space?
The Earth's atmosphere acts as a screen which affects the incoming light and makes the possibility of measuring very accurately the star positions rather difficult from the Earth. By moving above the atmosphere, we can measure these positions much more accurately. The second reason is that the environment above the atmosphere is very good for these kind of observations, both from a thermal point of view. We can have a very constant thermal environment on the satellite, and from the point of view of the effects of gravity on the instrument. The third reason is so that we can achieve an all-sky visibility. Measurements which are made from the ground can only be made viewing a certain part of the sky if you're in the northern hemisphere, or the southern part of the sky if your observatory is in the southern hemisphere, and we can only observe certain parts of the sky at certain times of the year from the ground. And this makes the construction of an overall system of positions and motions very difficult to achieve from the ground.
Hipparcos has been a major success of visible wavelengths. We've also had major successes in what we may call invisible astronomy, with, for example, IUE and IRIS. But let's not forget the advantages of space for conventional telescopes, which are unconventional only inasmuch as they operate from above the top of the atmosphere. 1990 saw the climax of one of the most ambitious space projects yet. I'm at the Johns Hopkins University in Baltimore, or, to be more precise, at the Space Telescope Science Institute. At the moment, this is one of the most important places in the scientific world. It's the nerve center of the most fantastic telescope ever planned, the HST, or Hubble Space Telescope. Operating from above the atmosphere, the HST has perfect seeing conditions all the time, which is why, even though it has only a 94-inch mirror, it can outmatch all the larger telescopes based on the surface of the Earth.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope.
It was a perfect launch. Once the telescope was in orbit, tests began. That, of course, was the moment when it was discovered that the mirror was faulty. And it was a most unpleasant shock.
Well, you know, Patrick, we used to say that this mirror is the most finely polished mirror ever built, and that's still true. We used to say that it was the cleanest mirror ever made, and that's still true. It's simply apparently machined the wrong shape. The prescription is incorrect by about 2 microns, which in English would be about 1/50th the width of a human hair. There are 2 ways to get around this particular problem. One way, which we are addressing now, is to use computer algorithms, or reduction tricks, in effect, to massage the images to remove the halos. It's a process of deconvolution, the $50 word, or image enhancement. The real way to solve this problem, of course, is to get back to Hubble and to put a series of corrective lenses and mirrors on the telescope to introduce an equal but opposite amount of aberration. That we hope to do within a few years with some astronaut help on board the space shuttle.
Objects of all kinds were imaged. Jupiter with its cloud belts. Saturn, obliging enough to produce a brilliant white spot at just the right moment. The cores of globular clusters, such as 47 Tucani, with the stars called blue stragglers. The light ring from the supernova in the large cloud of Magellan. And the effect of a gravitational lens, with the light from a remote quasar split up by a foreground galaxy to produce the Einstein cross, or cloverleaf. Well, you can see how much has happened during the 35 years since the Sky at Night went on the air and Sputnik 1 was launched. We've had satellites of all kinds, probes to the planets, men on the moon, and our knowledge of the universe has grown beyond all recognition. But what of the future? Probes are planned for Venus, Mars, Jupiter and Saturn. By the year 2000, we may well have permanent space stations, perhaps even a base on the moon. And think how quickly all this has happened. The first airman, Orville Wright, made his preliminary flight in 1903. The first man in space, Yuri Gagarin, went up in 1961. And the first man on the moon, Neil Armstrong, landed there in 1969. So in only 66 years, man has gone from being earthbound to flying to the moon. And now there are spacecraft traveling beyond the solar system. So I wonder what's going to happen during the next 35 years. I'm afraid that I won't be presenting the Sky at Night in 2025, unless, of course, I live to the advanced age of 102. But I'm quite sure that it's going to be dramatic. Here, from my little observatory in Chelsea, I've seen what's been going on, and I've tried to share it with you. Thank you for watching. But you know, although in this program we've seen many sophisticated spacecraft, I still have a soft spot for one that I personally test-piloted a few years ago. Well, as you can see, the design of this lunar bicycle, in which I'm riding at the moment, differs in certain important respects from that of the lunar rover, and is fairly obviously superior to it because it contains a number of features not previously incorporated. This, as you can see, works very much in the manner of a sweeper, and this is precisely what it is, and this will collect lunar samples for you. Next, we have the lunar boot. It can be used to plant the usual obligatory footprint upon the moon's surface, just in case the pilot is too tired to get out of his bicycle. But of course, future astronauts will in fact be able to incorporate these lunar bicycles, which do make the present lunar rover completely obsolete.